Okay, next I'd like to continue our discussion on queuing theory and discuss the simplest queuing model there, which is the single server model. And we're going to assume Poisson arrivals and exponential service times. So let's assume we've got a loading dock at a warehouse where this is the loading dock itself, and we've got one worker loading and unloading trucks, and this is the queue here. And let's assume that our lambda is 3 trucks per hour. That's the mean arrival rate. And that's what's Poisson distributed. And let's talk about our service rate then, mu, which is 4 trucks per hour. That's our mean service rate. So on average, we can service 4 trucks in an hour. Sometimes it's going to be longer than that. Sometimes it's going to be shorter than that. Okay, so these are just average rates. And notice that you're only going to use this model if lambda is less than mu. If mu is greater than or equal to lambda, you're going to have infinite queues right away. Okay, the first thing you should note, given these two, the lambda and the mu, and a bunch of the assumptions that we talked about in the last video, if you just invert these, 1 over lambda, 1 over 3, that's the mean time between arrivals. So that's in hours. So on average, we've got 20 minutes between arrivals. Well, sometimes it's going to be much shorter than that, sometimes it's going to be much longer. But on average, it'll be 20 minutes between arrivals. Likewise, on the service time, if we take 1 over mu, just invert it, we get 1/4 hours, or 15 minutes. So on the average, it takes 15 minutes to service our trucks, to load and unload them. And that's what's exponentially distributed. So that's the mean service time, 15 minutes. Sometimes it's going to take much longer and sometimes shorter. Okay, so given these two numbers and a bunch of assumptions, we can calculate a number of different things and then analyze our system. When I talk about the system, I mean the whole thing, the queue and the service. The first thing is rho. Rho is the average utilization rate. And you calculate rho by taking lambda over mu. So in this case, it's just 3 over 4, or 0.75. That's the utilization rate. So 75% of the time, this loading dock is busy. Well, it could be better, it could be higher, right? That would be a higher utilization rate, sounds better. But when you look at it this way, also known as, that's the probability that a truck must wait. So 75% of the time that a truck comes up there, they're going to have to wait in the queue, which is pretty high probability. Another thing we can calculate is then, related to this, is P sub 0, the probability of 0, or nobody in the system. Nobody's being serviced and nobody's in the queue. That's just 1 minus rho that we calculated here. 1 minus rho is 0.25. So 25% of the time, nobody's in the system. Generically, then, we can calculate P sub n for any n. P sub 1, 1 truck in the system. P sub 2, 2 trucks in the system, and so on. This is just calculated by taking 1 minus rho times rho to the n power. So in our example, for probability of exactly 1 truck in the system, and that truck is being served, it's 1 minus 0.75 times 0.75 to the first power, which is 0.8175. So 18.75% of the time, we've got exactly 1 truck in this system, and they're being served. Okay, next. 4 more things we'll calculate. L bar, which is the average number of customers or trucks in the system. That formula is just lambda over mu minus lambda. So in our case, 3 over 4 minus 3 is 3. So on average with this system, we've got 3 trucks. We've got 1 truck in the loading dock and 2 trucks in the queue on average. We can also calculate L bar sub q, which is the average number of trucks in the queue. To do that, you just take rho times L bar. This is one way to do it. L bar is what we just calculated. So 0.75 times 3 is 2.25. So on average, over the long run, we've got 2.25 trucks in the queue. Doesn't sound so bad yet, but wait till we get to the times. First, we can calculate W bar. W bar is the average time in the system. Okay, that's the queue and the loading dock itself. That's just calculated by taking 1 over mu minus lambda, which in this case is 1, over 4 minus 3 is 1. We're talking about hours, so it's 1 hour in the system. Finally, we can calculate W bar sub Q. The formula is rho times W bar, so it's just 0.75 times 1 is 0.75, or 45 minutes. That's the average weight in Q, 45 minutes. So, what do we do with all this information? Well, now we've got to trade off those costs that I mentioned last time, the cost of waiting versus the cost of service time. Okay? So what we have to look at in this case is what warehouse workers get paid in the Southwest versus what truck drivers get paid and the trucks that are just sitting there. Well, down here in the Southwest, warehouse workers might get about $10 an hour to load and unload trucks. Truck drivers are going to get paid a little bit more, and trucks are very expensive, especially if they're idling right now and all that gas is being wasted. Okay, so let's say that we could hire another warehouse worker, and so we'd have 2 workers at a loading dock, and we're going to increase their productivity. Remember, originally the productivity was that they could load and unload on the average of 4 trucks per hour. But what if we hired another warehouse worker and we increased the productivity up, not 100%, but maybe 50%, so that they could load and unload trucks, 6 trucks in an hour? What does that do to our statistics? Well, first rho in the system then, the utilization rate goes from 0.75 down to 0.5. So now, 50% of the time a truck must wait. Probability that nobody's in the system, as compared to 75% before. Of course, the utilization rate goes down, but when you think of it about the probability of a truck waiting, this is much better. L bar was originally 3 trucks in the system. Now it's gone down to 1 truck in the system. L bar sub Q, the number of trucks in the queue, was originally 2.25 trucks in the queue. It's gone down to a half a truck in the queue. And here's where it really gets good. The average wait time. Originally the average wait was 1 hour in the system. Now it's gone down to 20 minutes, and that includes the service time, so that's pretty good. And look what happens to the wait in the queue. The wait in the queue was originally 45 minutes, or 0.75 hours. Now it's gone down to 0.167 hours. What is that? That's only 10 minutes, the average wait in the queue. So I would say it doesn't take a rocket scientist to determine that, indeed, it's cheaper to hire a person for $10 an hour to work in the warehouse and have this system as compared to the other, because those trucks are going to be higher utilized, and those truck drivers are not going to be paid for just sitting there for long periods of time, and those customers are going to be much happier. So what it really comes down to is, who's paying these truck drivers? Are we paying them, or is somebody else paying them? Are they our trucks, or are they their trucks? What's our competition? Can they go to another warehouse, or do we have a monopoly? They have to come to us. These are all the kinds of questions you need to ask once you get the service characteristics of your particular loading dock or queue. By the way, the formulas I presented today here are a little different from the ones in your textbook. You can use those, you can use these. I think mine are easier, but it's up to you.